Okay, we're at about 18 folks, so I'm going to go ahead and get started now. My name's Greg Hyde. I'm the JMS Biohandling Product Manager. Today we're going to look at designing the right biosolids storage solutions. We'll look at dry biosolids and wet or dewatered biosolids. And that dry, typically out of a dryer at 90 to 95% dry solids, dewatered at as low as 15 up to 30% dry solids. We'll look at storage vessel types, key application and design variables, silos versus hopper volume, a project spotlight, and then conclude. On storage types, silos are cylindrical storage for dry and wet sludge, typically used more for dry product. Shape is strong and economical. Shop welded are available up to 14 feet, depending on location, to fabrication. Site bolted or anything greater than 14 feet in diameter. Site bolted are only available in carbon steel paint coated, typically powder coated. As you can see, both of these samples here are site bolted. Both utilize a 60-degree cone. The one on the left here is for dry biosolids. This is one that's going in Savannah right now, 21.5-foot diameter bolted. The one on the right is a bolted tank for dewatered sludge feeding pumps. So we've got conical to a bin activator over here, conical to a live bottom screws here. We'll take a closer look at dry sludge storage. JMS dried biosolids silos meet NFPA requirements for combustible materials. NFPA is National Fire Protection Association. That is looking at the combustibility of the dried solids. That value has to be determined by running tests
or environmental
and a Pmax value to classify the sludge combustion rate so that we can design the explosion rupture panels, which you'll see over here in the Savannah silo. We also utilize a nitrogen purge system, monitor temperature, carbon monoxide, and oxygen, have a dust control system. What you can't see here is the conical portion in either one of these. It's hidden in the skirt here. It's hidden under the platform here. But this will come down to a 60-degree cone with a bin activator on the bottom, rotary airlock. The Savannah will come down to one retractable spout to load a truck. In the case of the Wilmington job, we loaded a screw conveyor with 3 load points, 3 retractable chutes. Going back to the nitrogen, that nitrogen is when the temperature is monitored by the thermocouples inside the tank. When it reaches a set point of temperature or high carbon monoxide or high oxygen, we can purge that through nozzles in the conical section here to displace the oxygen in the top part of the tank. You can see here this is being fed by a drag chain conveyor with low volumes of sludge coming out of the dryer. This is all we need. It's a very flexible, relatively low cost means of conveying up to the top. And we'll look at silos for wet sludge. Not typically used for wet sludge because in municipal we're typically going to 304 stainless steel, and the larger silos in the bolted tanks are not available in 304. This is carbon steel only. You can see this example in Zellwood here. This was a large site bolted tank utilizing live bottom screws at the bottom that meter sludge to pumps for downstream process. Here's the isometric view without the skirt. Here's the actual photograph with the skirt that's supporting the silo here. This example here is a 304 stainless steel, one of 3 silos that will go into Palo Alto that's in manufacturing now. You can see that this is a small to medium size. Don't have the cubic yards, but you can see that this utilizes a leveling screw. It also goes from round to rectangular. This shape gives much better flowability to sludge than just going conical here. This tends to neck down the flow and funnel it, where this gives a much higher rate of flow down to your live bottom screws. Live bottom screws are not shown here, but these live bottom screws have multiple gates for truck loading. So we have 3 of these tanks lined up in a row with multiple truck lanes. You can also see that because the conical section is flattened out to go to rectangular, it requires stiffeners in this area. And we'll look at hoppers, rectangular or square storage vessels for wet sludge. Many of the smaller to medium size are shippable on a drop deck, depending on overall height. Sometimes they can be broken into a couple of pieces for site welding, or when you get into some massive structures, it may have to be completely site welded at the site. If we look at this example over here, this is wet sludge for Allen, Texas. This is about to go into manufacturing. This has not been manufactured yet. And you can see, just looking from the top down, we've got a redundant conveyor system going up. This system is all shaftless. We've got redundant system up here to feed either of the distribution conveyors. We've got distribution conveyors at the top with 5 drop points, multiple gates. We have sensors reading the levels of the sludge to distribute the sludge in the lower point of the hopper to utilize the fill rate. You can see the external stiffeners that are required to maintain the shape of the tank. We also utilize internal tension bars going across internally. This greatly reduces the amount of reinforcement steel on the outside, and when you're talking about this much 304 stainless steel, that's an important factor. This system also utilizes load cells, so the input can be read and monitored. What you can't see here is 3 live bottom screws under each conveyor, multiple gates for truck loading. This other example is for Dallas TRA. This is pre-THP process, pre-combi. Cambi system, so this sludge is about 15 to 18% dry solids, pretty fluid. So this utilizes one common tank broken up into 3 sections with a single screw. Since the sludge is so wet, we're going with a single screw here, whereas on the larger hoppers, we're using the multiple screws to prevent bridging or rat holing. The single screws here feed a single pump under each section, and there are 2 of these hoppers, so there's 6 pumps. Again, you can see the reinforcement here, single screw and a knife gate to isolate the pump that's underneath. Good place to talk about slide gates. Over here on the gravity drop from the large hoppers into the truck, we utilize heavy duty JMS slide gates that are anywhere up to 3 or 4 feet wide by at least that long. These are designed to take the head pressure of the sludge above when closed and then actuated. We typically use electric actuators. That's what we prefer. Hydraulic and pneumatic have been used. But going back over here to the knife gates that are under this, we utilize knife gates here because this entire column is under pressure when the gate is open. That takes a special knife gate seal, a bidirectional seal. We're utilizing a Zurich knife gate design for that. Different applications, different gates. Put in an example here of an FEA analysis we did on a very large hopper that the client was requesting 4 vertical columns to look at the stress loads. Better idea, look at these are almost the same volume, and these have 10 vertical columns versus 4. Better design over here. This would have had to be substantially reinforced in the shell to handle the load versus using columns on this side. The other vessel type is bins, which is what we're calling an open or retractable top storage, and typically that's truck receival bins to accept foreign sludge from other plants. Typically it's going to a plant that has an incinerator or THP process. They're bringing in, they have excess capacity, and they're making money by bringing in sludge from other plants that may be hauling that off. And you can see that here are 2 that utilize leveling screws, which are these screws going through the hopper here. Here's a top view of those leveling screws. And the reason we're doing that is we were required to get a certain volume in this vessel that, with the limited depth of the pit, and given that we had one load point, we had to work around the geometry. We had to widen the stance by putting in 4 screws in the bottom to gain that volume, and the cross-sectional area got wider. We also put the leveling screws to draw up sludge from the truck side. We also used a full pitch live bottom screw so that that sludge is being taken away from the truck side first, so that we could utilize more area, usable area of the tank. Occasionally we'll do small bins. Grit and screenings typically are smaller volumes. You've got may have a day bin that's only a few cubic yards, say up to 5 or 10 cubic yards with a single gate underneath. And we'll look at some of the key variables. Application and design variables. Product related, of course, we need to know what is the product and the angle of repose. Angle of repose being important to getting to that usable volume and calculating that. And unless otherwise indicated, we assume 45 degrees on dewatered sludge and 35 degrees on dry sludge. And site related conditions, of course, we need to know seismic, wind load, if applicable. Surprising amount of these structures are inside, so the wind loaded doesn't factor in, but we also have height restrictions, whether that's inside or outdoors, depending on some building codes. Then design related, the number one driving factor here for starting the design is usable storage volume. How much do we want to store? Whether that's 1 day or 2 day, whatever that volume is, we need to know that, and that's calculated with the angle of repose and loading method and feed points, which we'll talk about in a minute, and the loading method. Then we need to know about loadout type. We're going to trucks or pumps or conveyors. If we're going to trucks, how big are those pumps, the trucks? A lot of people assume it's going to be a 40-foot trailer, but a 40-foot trailer will not even fill up before it's overweight with dewatered sludge. A lot of the trucks are 24, 27 feet long. So we need to know the typical truck size so that we can place those gates and consider our live bottom configuration. The volumetric capacity of the screws, that's not a problem because these live bottom screws typically have more capacity than is required. and then system requirements as far as ladders, sensors, gates, load cells, and controls. This is comparing a silo to a hopper that have similar capacities. As you can see on the left, we have a hopper that is representative of Wilson Creek, Allen, Texas job at 450 cubic yard as compared to a 421 cubic yard dry silo for Atlanta that we're working on now. And you can see that the dry silo at slightly less capacity is 30 feet taller than the hopper. Both have to utilize the 60-degree slope on the bottom side, getting down to either the live bottoms or the bin activator. You can see where the most effective storage area is going to be on the straight wall side of on the storage. Of course, we have to use the slope to get up to that point to where it's sufficient to use that straight wall. You can see on the hopper, we're using a distribution screw at the top, as we did in Allen, Texas. This can also be done if there's not a distribution screw. If there's one or two loading points from, say, a pump, we can go into a distribution screw on top, or we can utilize a leveling screw internal of the hopper. Speaking of storage area and straight wall efficiency, this is 450 cubic yards usable. If we were to just extend these straight walls up 15 feet, we would double the capacity of this hopper, just because that's where your most effective storage area is in the straight wall here. As typical with the storage hoppers, we're using 304 stainless steel for the vessel, and the exterior reinforcements, we use carbon steel hot dip galvanized for the heavy columns, because the I-beam availability and cost in 304 for I-beam is not acceptable. This early sketch was representing a shafted screw. Live bottoms, let's talk about that a little bit. You can see that this is 40 feet long at the top, and we've necked this down a bit to 30 feet at the bottom, and that's because we always want to minimize the length of the live bottom screws if we can, for several reasons. Cost, minimize the mechanical equipment as much as we can. If we're going with shafted screws, 30 feet is about the practical limit of where we want to be on live bottom screws with the shafted screw, because of the deflection in the rotor shaft. This already gets very heavy and large, and the larger and longer you go and the larger diameter, the larger your drive shafts and your bearings and all of your other mechanicals get, and so does the cost rises exponentially. So we want to keep the length of this in check if we can. Even going shaftless instead of shafted here, we still want to keep that to a reasonable length for several reasons. Shafted versus shaftless on a live bottom screw, that's a whole other discussion, but because of the liner accessibility, we prefer to go shafted on live bottom screws. So, just to recap, when we're looking at hopper design, start with usable storage goal. Look at our height restrictions, look at our clearance requirements, feed in and feed out methodology, and then try to work the geometry around that. So a lot of factors go into how we start and how we end up with those designs. Now we'll look at a JMS spotlight. This is the Blue Plains plant in Washington, D.C. It's one of the larger wastewater treatment plants, I believe, in the world. This is the largest THP facility in the world, first combi system in the U.S. JMS put in 400 cubic yard biohoppers pre-THP process. They're used to store and meter sludge to pumps that fed the THP process. You can see the plant here, the Canby process. I believe we're in this building here. Here you can see 3 of the 4 hoppers here, and live bottom screws going in. You can see the variable pitch here. We're starting at a low half pitch here and progressing to full pitch or larger out on here. What that does is that picks up sludge incrementally across the cross section of the hopper, so that you're drawing down sludge from the whole cross section rather than grabbing from one end and pulling to the other. This also meters out of from underneath the silo, the hoppers, and drops into the pumps below. We also supplied post-THP belt conveyors to distribute sludge for haul-off. This plant was a great success. They create a Class A sludge that is marketable, and it has greatly reduced the carbon footprint of the plant. Looking at the overview, JMS Biohandling offers all storage system solutions: silos, hoppers, bins. We offer NFPA design and rating for dry biosolid storage, VFD drive live bottom screws, large heavy duty outload slide gates, leveling screws, load cells, load sensors, level sensors, up and downstream conveyors, and control. We offer total system responsibility from an experienced design and manufacturing team. I appreciate your time. It's like we're finished about 3 minutes early. If anybody wants to stay on, you got any Q&A, be happy to take any questions. Thank you.